Yeah, so I guess we're suffering a bit from the concurrence of Quick 3D, but yeah, that's the way it is. So we're going to discuss about what's new in Quasar and what's new in Qt3D. We start with the Qt3D part. So what did we do for Qt3D in 5.14? We made a few changes. A few changes in the backend of Qt3D, as well adding new API to the user, but we will first discuss what were our motivations for the backend changes we made. So essentially what we decided to do was to try to improve performance, mainly CPU usage, and to make maintenance of the project a bit easier over time. And to do that, we first have to have a quick look at the threading architecture of Qt3D, in 5.12, 5.13. Essentially what we had at the time was the main thread where users would create their node of entities and components. That would be the user-facing part. Then we would have the aspect thread where aspects would live. That's also the place where we would have our simulation loop. The simulation loop essentially is the game loop you will find in a typical game engine. And on top of that, we also had a thread pool where each aspect can launch jobs. And optionally, if you're using the render aspect in Qt Quick, if you're using Qt Quick, you get the scene graph rendering thread. If you're using Qt3D, you get a render thread. We would have that thread to submit our OpenGL comments. So that was the way it was at the time. Motivations for the aspect thread were, well, if the user starts blocking the main thread, maybe Qt3D can still be going on, playing animations, and things will be well. Turns out we realized that most of the people were using Scene3D to drive the Qt3D rendering. Scene3D has a locking point, and that meant that the aspect thread was locked with the main thread every frame. So if you were to lock the main thread, you would also lock the aspect threads, which in a way defeated the purpose of even having that thread in the first place. So what we did was actually remove that aspect thread. So now aspects live in the main thread as well. And we also have the simulation loop in the main thread. That gives us a few interesting benefits. One of them is it's easier to maintain. We've got less chances of having race conditions. And also, it makes it a lot easier to control the Qt3D run loop. What I'm trying to say with that is that in the past, with the aspect thread, Qt3D would be handling its simulation loop internally. And if you wanted to tell Qt3D, well, please do the rendering right now, that wasn't possible. This is now fixed with that aspect thread removal. The other thing is that part of the work was also motivated by looking at what we'll need to do for Qt 6 and maybe a possible integration with the abstract rendering abstraction. The other nice benefit from that is let me get back to the drawing. Each aspect had to maintain a backend copy of the front-end scene, right? So if you look, each aspect right there has its own copy. And to maintain the two trees in sync, we had to send, anytime a property would change, we had to send string-based messages with Q-variants containing the values of the property. We would store that in the change arbiter, and every time this simulation loop would go to sync changes, we would apply those string-based messages. Well, turns out that it's not even required anymore, because if both the front-end and the back-end trees live in the same thread, we can just look directly on the front-end node to detect what has changed. Okay? That's a bit an internal implementation detail. The nice thing, however, when we've measured on lots of entities, so if you've got a really large scene where you're playing animation on each entities, before using the string-based message approach will cost us 12 milliseconds per frame. We're now down to 4 milliseconds, so that's a nice improvement in that area. So that's, I'd say, the major changes we made in the internals of Qt for 5.14. Now the question is, what are we going to do next in Qt6? Is Qt even going to be there? Well, for now, it's going to remain. What we're really wondering, and that's the big question, is how do we handle the modern graphics APIs? Or are we going to handle Vulkan Metal? Right now, we're considering two approaches. One way would be to use RHI. It has a few limitations for what we're trying to do with Qt3D. So the other option would be to say, well, let's make a render plugin for each graphics API. That's a lot more work, but that gives us, a lot more flexibility when it comes to using all the features we want from Vulkan or Metal. So we've still not decided on that yet. We might end up, I guess, probably with an approach where we have an RHI-based backend for most of the cases, and if you need more performance, maybe it might make sense to have dedicated render threads for render plugins for that. The other thing we're wondering for Qt6 is, well, we're thinking about changing the way you will describe the frame graph in Qt3D. The frame graph is the way you describe how you want your renderer to do, to behave, and what you want it to do every frame. And right now, we've got an API which is a tree-based API. So you're creating a viewport node, and you're adding children such as, I don't know, first-term calling if you want first-term calling. You could add render states and so on. It's nice. The only issue with that is that it's really hard for us to optimize that, because in order to know what you want to render, we need to traverse that entire tree. And the other disadvantage is that it makes tooling around that a bit difficult to implement. So what we're thinking about is having still a frame graph, but having a linearized description. So what basically that will mean, we will end up with something called a render stage. And in that render stage, we will specify the size of the viewport we want to use, the frame buffer we want to use, the, I don't know, the filtering we want to use. All of that will be specified in one central place, and that will make optimizations and tooling around that a lot easier. And lastly, one thing that might be interesting for users would be a way to get access to some of the rendering information, such as the number of triangles being drawn, the number of vertices in memory, the memory usage being used by your buffers or your textures, so that we don't get more complaints about, well, I don't understand why this is slow, what's happening. You will be able to get a small idea of what's going on with such information. At least that's our hope. But yeah, we'll see. Now, the part where you might be a bit more interested is the new additions in the API for 5.14. So we made quite a few changes there. First, let's start with Scene3D. Scene3D, we've added an underlay mode. So if you've seen other talks with Quick3D, actually, they will also have a similar mechanism. So what happens with Scene3D? Scene3D is the way to integrate Qt to integrate with Qt. What we do is we render the Qt3D scene into an off-screen surface, and then we ask Qt to render a rectangle on which we display that surface. That's the way it has been until 5.14. We now have an optional mode you can use, the underlay mode, which essentially uses the Qt window before rendering signal to directly render the Qt3D content on screen. So that's nice to have on some low-end embedded hardware where using frame buffer objects is a bit too much for what they can handle. The other thing we've added is Scene3D view. And the need for that Scene3D view is the fact that every time you're instantiating a Scene3D, you're also instantiating the whole Qt3D engine, the aspect manager, the thread tool, obviously lots of resources. So if you instantiate several Scene3Ds, you're instantiating all of that all the time. Instead, what we've done with Scene3D view is you create a single Scene3D, and then you can have as many Scene3D views as you want, so that you only create the resource-intensive stuff once. When it comes to the frame graph, we've added quite a few things as well. We've got the QNoPicking node. That's a way to prevent having any picking done in a branch of your frame graph. So typically, if you've got two viewports, there might only be one viewport where you want to select objects, while you don't want anything to be selectable in the secondary viewport. With the QNoPicking, you can disable selection on that second viewport. We also, Ford contributed something called the QSub-tree enabler, essentially that allows you to enable or disable an entire branch of the frame graph using a Boolean condition. QSort policy, if you're not familiar with that one, QSort policy allows you to specify how you want your draw calls to be sorted. Do you want your draw call to be sorted from back to front? Or do you want them to be sorted by, I don't know, the shader being used? That you can do with QSort policy in order to minimize the amount of OpenGL calls being generated. And we've added a new mode called texture, which allows you to sort commands by textures so that all the draw calls that use the same textures will be made, and then you'll switch on to the next texture and make all the draw calls that rely on that texture and so on. That avoids the case where you bind a texture, you make a draw call, you bind another texture, you make a draw call, and you realize that, whoa, we're shuffling draw calls where we could just be binding the texture once, drawing all the draw calls that need that texture, and move on to the next one. Next thing is QTransform. QTransform specifies a local transform in Qt3D, which works fine. The issue is when you've got a large hierarchy of Q entities. If you only deal with local transform, it's hard to know what's the actual position in the world of an object. And to solve that, we've added the world matrix property. So you can use that to actually know at which world position your object is. QTexture. QTexture, two nice things with that. First, we have the compressed texture support with KTX. So I think ASTC algorithms, compression algorithms. But maybe more interesting is QTexture data update. QTexture data update is an API so that you can update only part of a texture. And that's also useful in the case where you need to allocate a texture that has more than 2 GB of memory size. Why? Because we based our initial QTexture API on QByte array. QByte array is sized by the size of an int, 32 bits. So once we reach that limit, we cannot go beyond that. So QTexture data update offers you a way to load, in a way, your texture through several calls, but allows you to go around that 2 GB limitation. Next, QShader image. QShader image adds OpenGL image support, so really useful when you're working with compute shaders, typically, so that you can atomically write or read into textures. And finally, QObject Picker. We've added a new picking mode called nearest priority pick. And the idea behind that one is, let's say you've got spheres lined up, right? And you're launching a ray through these spheres to select one of them. In some cases, you might want to say, well, if that sphere is in the line of that ray, in the intersection path, I always want it to be selected. And if you want to handle that case, even if there are fields in front, with the nearest priority pick, what you can do is assign to each QObject picker you have a priority value, and it will select the object on the array path, which has the highest priority. That's really useful when you're dealing with, let's say, 3D gizmos, and you click on an object, your 3D gizmo appears, and you want to make sure that even if there's something in front, you're always going to select your gizmo. And that pretty much concludes all of the changes we did in Qt3D. So it would have been nice to have time to show you all of that, but yeah, only 25 minutes, so let's move on to the next part. And the next part is talking about Quasar and what's new in Quasar. And let's first do a quick recap about what Quasar is. And it's easier if we start with the actual diagram. Quasar is an integration workflow we've been working at KDAB for the past couple of years. And the idea is that Quasar is going to allow you to integrate with the work done by designers well, it's going to be a lot easier than if you rely on doing it yourself. So first, Quasar is built on top of Qt3D and divided into two main parts. We've got the runtime in Quasar, which is a fancy word to say that we've got a GRTF2 loader, and we're providing tooling around GRTF. So the idea is a designer is going to create all of his model in Blender, Maya, whatever tool is familiar with. Is going to export that into GRTF, GRTF2. We're going to provide tools to optionally introspect the GRTF, compress some parts, tell some textures to be compressed or not. And you're going to use the Quasar runtime built on top of Qt3D to load that GRTF2 file. Okay. The nice thing is we're going to load that GRTF2, create all the Qt3D elements that are required, and then you're going to be able to pretty much use your application as if it was native Qt3D development. So let me check. Yeah. If you want to try it out, it's on GitHub. We've got nice documentation, examples, and there are different types of licenses available to suit most of the needs you might have. Now, what can we do with Quasar? We'll do a quick demo later on, but let's go over the main highlights. First, it runs on anything above or equal to 5.12.5. It has C++ and QML APIs, and it also has Python bindings. I'd say that maybe the most important feature in Quasar is the GRTF2 importer, which is fully GRTF2 compliant, which means you get access to physically based materials, you get access to skinned, morph, and keyframe-based animations, and we also handle some optional extensions such as the Draco compression. That means pretty much all of what the designer creates in Blender, let's say, from animation to the actual visual thing he's seeing on screen, you would get, let's say, 90%. There are some changes in the implementation we do think, but you would get 90% of what you're seeing in Blender into your Qt3D application if you're using Quasar for that. On top of that, Quasar also provides you full screen post-processing effects. So you've got the regular Gaussian blur, you've got depth of field, you've got tone mapping. We also have the opacity mask. And finally, the nice thing is when you load everything with the GRTF2 importer, we feed what we call asset collections. So essentially tables that you can use to retrieve a given type of asset. And I'm going to show you in a minute what it looks like. So that's for the runtime part, the library built on top of Qt3D. Next, we've got the tooling side. And right now, we have three main essential tools. The GRTF editor, which allows you to open up a GRTF2 file, look at what's inside, look the names of the different assets, have a preview of what the file looks like. That might be a way for you to say, detect if animations have been exported correctly, if the skeletons are fine or not. We also have a simpler tooling called the GRTF viewer. Essentially, that one just tries to display a GRTF2 file. And finally, we've got an asset processor. That's a command line tool which you can call to decide whether you want to compress a GRTF2 file more or less. And that one, that cube map to octahedral map, is something we created to convert a cube map texture to a texture 2D 2D texture, which is required to have physically based materials work on ES2. There's no way around that. Now let's do a quick demo. Should have time, and I'll show you the idea behind Quasar. So that's the car scene from our example. So that's an official example. If you download Quasar, you get that stuff as well. And we're essentially displaying a car. That car has a few animations baked in. We can, what else can we do? We can move the walls. We've got skybox, so we are showing the skybox. You can switch, the skyboxes where you're using HDR rendering to show, to have a bit more precision in the highlights and the shadows. Everything gets reflected on the car. And we also have a way for you to try a couple post-processing effects, such as the bloom effect. So the bloom effects, you can specify the threshold value to get more or less bloom, and you can specify the number of passes to be used to, to get the effect you want. The more passes, the more costly it is, but the nicer looking as well. We've got that. We've got ways to play with the exposures, but that demo really shows you quickly what you can do with Quasar. And if we look at the actual code, what we did was essentially start from a regular Qt Quick UI, into which we've used the Scene3D from Qt3D to load a main scene file. And that main scene file then does the Quasar imports, creates a scene entity. A scene entity is a regular Qt3D entity that contains asset collections. And we're going to see in a minute what those might be useful for. So we create our root entity, then we create, let me check where the frame graph is. Right. We do typical Qt3D stuff where we specify the frame graph to be used, and we use one of the default frame graphs provided by Quasar, the forward renderer. And that one essentially allows us to specify which camera we want to render the scene with, what type of post-processing effects we should apply, whether we want back to front sorting to be enabled, which might or might not make sense depending on whether you've got transparency or not in your scene. And finally, you can specify which tone mapping algorithm to use by default. So the rest is, if you've been using Qt3D, the rest should be pretty much familiar. So nothing really interesting except for that part. That part is where we're instantiating the GRTF2 importer. We're specifying the scene entity, the entity that contains the asset collections, and specifying the source path, which will load the GRTF, where our GRTF2 file is, sorry. Once we've done that, we can create assets, and we have one there. We can create a Quasar asset and specify the name of the asset we want to retrieve, into which collection, and that object, we could manipulate it directly as if it was our camera directly. We can do the same thing with animations, but with animations, instead, we've got something a bit easier to handle called the animation player. And that one, you can directly specify the name of the animation clip, the scene entity, and the number of loops and wherever the animation is running on it. Now, you might be wondering, how on earth am I supposed to know that the animations are named that way? Well, that's where the GLTF editor we provide becomes useful, because the GLTF editor allows you to select any kind of GLTF2 file, opens it, introspects it, gives you the name of all the animations. You can decide to play them if you want. To get a preview, you get the list of all the entities created in the entity collection. You get a list of all the meshes created as well. Or you could also just go on the car and try to click on some part, and it will select for you automatically the mesh that's behind your mouse. That gives you then details about which buffer is being used, which attributes are being used. So you kind of get the idea of that tool allows you to know what type of Qt3D resources are created, what are the names, and then later on, when you implement your application, you know exactly what to retrieve. We also have support for looking through different cameras, and you can, in Blender, if in Blender you've animated the camera or made some more animations, they play back automatically because they are baked into the GLTF2 file. And you've got control then on the clock speed of those animations, where you want to play them faster, slower, or reverse them by using a negative time as your clock speed. So yeah, that's pretty much a quick tour of what you can do with Quasar. And yeah, now it's time for questions.
So any questions? And even if you don't have any questions, we are in the fortunate position that Paul is not going anywhere because he's going to have another talk. So yeah, there's the option of asking things later as well.
Yeah, and sorry if that bored you to death or was a bit too quick, but yeah.
No, I think that was a pretty nice presentation, and I also kind of like that you talked about the Qt 6 stuff and all those things. So yeah, it was quite interesting to me, at least.
At least so. At least one person should be happy from that. So. Good enough for me.